Welcome. This is the presentation of paper 886, DNets Equilibrium Grid Shell Layouts Symmetric to the Principal Stress Directions. The research was conducted by Eike Schling, Jonas Schikore, and Thomas Oberbichler as a collaboration of the University of Hong Kong and the Technical University of Munich. It is widely accepted in the architecture and engineering community that the principal stress directions are the optimal orientation for grid shell members. Morse circle is the common diagram to illustrate the stress on a continuous shell. The minimal and maximal stress N1 and N2 are situated 90 degrees from each other. The shear stress tau is 0 along these principal stress directions. When applied to a grid shell, the principal stress directions indicate the shortest path of loads to the supports. This also is the optimal layout to omit any stress of diagonal bracing for this particular load case. The quadrilateral grid shell is at equilibrium. But there are constructive challenges to this layout. It creates a heterogeneous distribution of stress in which the member taking the maximal load is prone to buckling, while the minimal direction is not used to its full potential. This is usually resolved by creating a hierarchy of members, as you can see in the brine bath and Dürrheim. Many grid shells profit from a homogeneous layout with standardized profiles, not only for its aesthetic value, but also for simplification of fabrication and construction process. In case of the multi-hull in Mannheim, it was of utter importance that all members were equally elastic in order to bend into the funicular shape. Frei Otto and his team systematically investigated funicular equilateral grids using physical hanging chain models to find their equilibrium shape. They discovered a particular effect to analyze domes and shells. When inserting a diamond mesh at each node, we can beautifully visualize the ratio of meridian and ring forces. For a semisphere, such as this analytical hanging model of the Pantheon, the diamonds show a gradual decrease of ring forces from the pole upwards. Above 52 degrees, all diamond meshes are then closed. We are interested in the design potential of this particular orthotropic effect. We are looking for equilibrium shells which distribute forces equally to neighboring members. We propose a novel grid shell topology of diagonal nets, DNets, that follow a path symmetric to the principal stress directions, and thus visualize the ratio of forces and create a natural flow of members towards the supports, similar to these precedents. Of course, we can find such nets, at least for rotational surfaces, just like Frei Otto did through funicular experiments. However, we don't have control of the shape, which usually ends up as a funnel. We are more interested in an analytical approach. If we look at the node equilibrium of a grid that is aligned with the principal stress directions, we can deduce very simple formulas. The vertical member FA will take the full load N1, and the horizontal member will carry the full load N2. This setup is always at equilibrium, independent of the ratio of height to width, nor the sign of N1 and N2. Now, if the edges are symmetric to the principal stress directions, there is only one angle that results in an equilibrium configuration. That is if the inclination of grid members corresponds to the ratio of principal forces N1 and N2. So for point loads, this is simple trigonometry. For surface loads, we have to consider the width and height of the loaded area. This equation only works if both principal stresses are of the same sign, so compression only or tension only grid shells. Interestingly, we can graphically deduce these directions using Moore's circle. If we draw the tangent from the origin to the circle, we find the square root of N2 times N1. We apply this formula to a continuous shell. We use isogeometric analysis in key V3D, rhino grasshopper, to calculate the undeformed and deformed surface of a shell under constant surface loads, and calculate the principal stress trajectories at any point without the need for interpolation. With this information, we can run an algorithm that step by step traces a path along the d-net trajectories, following the ratio of principal stresses. If the two principal stresses are of opposite signs, the d-net path naturally converges with the principal stress direction. As expected, this happens below 52 degrees on a semisphere. In this case, we add horizontal rings to complete the quadrilateral network. We first modeled archetypical rotational surfaces, such as a dome, a paraboloid, a cone, a cylinder, and a hyperboloid. This allowed us to verify if the layout corresponds to the meridian and ring forces. Typically, d-nets create a gradual shift of inclination towards the supports, as you can see in example D and E. Just like the Pantheon, the semispherical dome shows a transition from compression to tension ring at approximately 52 degrees, as we've just discussed, and the opposite behavior is exhibited by the hyperboloid with tension rings at the top. Finally, we conduct a structural analysis of three grid topologies: equilateral, principal stress aligned, and d-net. The grid shells are modeled discretely with pin joints and diagonal bracing to exclude any bending and shear forces. The profiles are constant within each grid. They are chosen to create the same total mass for all three. We investigate four load cases: self-weight of the structure, the surface load, the wind load, and all the combined loads. To get a holistic understanding of their performance, we use the tra value introduced by Frei Otto to calculate the load transportation as a total sum of forces through the structure. This tra value is independent of grid density, and it's a good indication of the efficiency of the structure. For self-weight of the structure, we can see that the principal net is at equilibrium with no forces in the bracing. This is not yet true for the d-net, which was designed for homogeneous surface loads. So for this load case, the d-nets are also at equilibrium. Neighboring members are utilized homogeneously, and there are no ring forces. This verifies our hypothesis. The efficiency of this configuration is illustrated by the low tra value. Interestingly, the d-net structure performs especially well under wind loads, where the diagonal layout offers efficient bracing and the lowest tra value of all. This analysis helps us to judge these particular layouts in a more holistic way for varying loads. Apart from the load transfer, we also investigated the stiffness of these structures by simulating the first eigenmodes based on self-weight and cladding. In this case, the D-net shows the lowest stiffness, particularly in the lower areas where member angles are acute. So far we have focused our research on rotational surfaces to test our method and evaluate the structural behavior of D-nets. Creating D-nets on free-form surfaces is not as straightforward, as the path and density is highly dependent on the shape and supports. It requires an additional step of post-rationalization to include the singularities and regions of positive stress ratio. Another promising approach for this beautiful problem could be through discrete optimization of quad meshes, as been investigated by David Pillay and Helmut Pottmann. We intend to intensify our research for D-nets and propose free-form solutions for design and construction. Thank you.